Hello, my friends. You could have been wondering why you need to study logarithms and indices. So, in this simple discussion, we'll be looking at the practical applications of logarithms and indices. So, logarithms and indices or exponents have various applications across different fields, and here are some key areas where they are used. So we have mathematics and computing. In solving exponential equations, you need to understand that logarithms help in solving equations where the variable is in the exponent. So when you find problems like 2 to power x is equal to 16, you can only solve this if you understand the rules of logarithms and indices. And there are very many practical applications or mathematical models where you need such um, a simple calculation. Then in a computational complexity, these are advanced applications in computing. So you'll find that even as you advance in mathematics, you understand the big O notation, and all these operate on logarithms. Then the floating point arithmetic, you find that logarithms help in computer calculations for large numbers by converting multiplication into addition. So that's how the computers understand some of these things. The logarithms help the computer in handling large numbers by converting them into multiplication and addition. Then in engineering and science, you find that in signal processing, we use logarithms in decibels to measure sound intensity and signal strength. So also pH scale, we use a logarithm. You find that pH is given by negative logarithm of the concentration of hydrogen ions. And this is to tell you the acidity of a solution, and therefore you need a logarithmic scale. If not, then you just take the concentration, the negative logarithm of the concentration of hydrogen ions. Then earthquake measurements, we use the Richter scale. This uses logarithms to express the magnitude of earthquakes. In finance and economics, we use compound interest, exponential growth models. Here, of course, in the compound interest, we have exponential growth model. So this describes the interest calculations. Then in stock market and inflation, the exponential and logarithmic models help in financial forecasting and analyzing inflation trends. In physics and astronomy, we apply logarithms in radioactive decay. So you find that the half-life of substances is modeled using logarithmic decay functions. And therefore, you need to understand the rules of logarithms and indices for you to do modeling, especially when you're talking about radioactive decay. Then star magnitude, the brightness of stars is measured on a logarithmic scale. In biology and medicine, the population growth of bacteria and cell populations often grow exponentially, and therefore, this is an application of logarithms and exponents or indices. Then pharmacokinetics, this is in a drug concentration, that is in medicine, the drug concentration in the bloodstream follows an exponential decay. That as time goes by, the concentration of drug in the bloodstream decays away exponentially. So modeling that requires you to understand the rules of logarithms and indices. Then in cybersecurity, where you talk about cryptography and security of computer systems, you find that the public key encryption logarithms are used in encryption algorithms like the RSA and Diffie-Hellman key exchange. Then hashing algorithms, you find that the logarithmic functions contribute to secure password storage. So these are a few applications of logarithms and indices, and therefore as an advancing mathematician, as you study, you need to really put more emphasis, you need to put in extra energy. So in the next discussion, we'll be looking at the different rules and a few examples on how indices can be handled. Hello, my dear friends. Welcome to this discussion. In our past discussion, we talked about the applications of logarithms and indices and why we need to study them and understand them. So in this discussion, we are going to be looking at details of rules of indices, and we shall be looking at examples. So indices will be of this form. You have A power B. Assume that you have such a thing on your paper. So what is A? A is called a base and B is called a power or an index or an exponent. So if I say A exponent B, I'm as well saying A is raised to a power of B, or A has an index of B. So the first rule that we are going to talk about is the multiplication. If I have, for example, let me use x to power A, then I'm multiplying by x to power B. This is the same as saying x to power A plus B. And this is true if you have same bases. If you don't have similar bases, then this doesn't hold. That is one. Two is that when I'm dividing this, for example, I have x to power A divided by x to power B, or x to power A divided by x to power B. This is the same as saying x to power A minus B. As long as the bases are the same, that is a condition. Number three, if I have x again to power A, then I create a bracket, then I say to power B, this is the same as saying x to power A times B, so which is equal to x to power A, B. Next is that if we have x to power negative A, this is the same as saying actually 1 out of x to power A. Number 5, if I have x to power 1 out of A, this is the same as saying taking eighth root of what? Of x. If I have x to power negative 1 out of A, this is the same as saying 1 out of x to power A. 1 out of A. And this is the same as 1 out of the eighth root of x. I'm saying eighth root of x. Next rule, if x to power A is equal to x to power B, then A is equal to B. If x to power A is equal to y to power B, then you cannot say that A is equal to B. So A is not equal to B. So as long as the bases are similar, then these powers are going to be the same. The right hand side must equal to the left hand side. The right hand side is equal to the left hand side. That's what I'm saying. Or the left hand side is equal to the right hand side. Let's look at examples. If I have y to power 13 times y to power 4, this is the same as saying this is y, they are same bases, to power 13 plus 4. And this is equal to y to power 17. Good. If I have 2 times y to power 13 times 3 times y to power 4, this is the same as saying 2 times 3 then times y to power 13 times y to power 4, which is the same as saying this is 6 to power 13 plus 4, so this becomes y to power 17. Let's move. If I have 2 power x, 2x to power 7 times 5x power 4. This is the same as saying 2 times 5 times x power 7, then times 5 to power 4. And this is equal to 10 times x to power 4 plus 7, that is 11. Now, what if you have y to power 13 divided by y power 4? This is the same as saying y power 13 minus 4. And this is going to equal to y to power 9. Or another one can say y to power 13 is equal to y times y times y times y 13 times. But if I make times to power 4, I can say now this is going to be times y to power what? To power 9. Then divided by y times y times y times y. So all this will go, and I'll have y to power 9. If I have 12 times y to power negative 3 times 4 times y to power negative 2, this is the same as saying 12 times 4 times y to power negative 3 times y to power negative 2. So this becomes 48 times y power negative 3 then plus negative 2. So this is the same as 48 times y to power negative 5. What if I have 7y to power 4? This is the same as 7, this is 7y to power 4 then raised to a power of 2. This is the same as saying 7 squared times y, okay, power 4 times 2, or raised to a power of 2. So this becomes 7 squared times y to power 8. This is 49y to power 8. So this is a very good introduction to indices. So if you also had 8 to power 2 out of 3, what would this equal to? This would equal to, first of all, this is 2 to power 3, because 8 is equal to 2 to power 3. So we are raising it to a power of 2 out of 3. Remember, we said this is the same as saying if you had a to power n raised to a power of m. This is the same as saying this is a to power m n. So if I do the same here, this will be 2 power 3, then times 2 out of 3, which becomes this and that will go, and I remain with the 2 squared, which is equal to 4. If I had 9 to power a half, this is the same as saying this is 3 squared. Always strive to make sure that you create some base raised to a power that is equivalent to 2 here, because if I raise it to a power of 2, then it would cancel with this and it makes my life easier. So which number can I raise to a power 2, then I'm able to have it still equivalent to 9? It is 3 squared. So I'll have 3 squared times 1 out of 2. So this and that will go, and I'll have 3. So this is the same as saying square root of 9. This is how we write square root. But because usually if we don't indicate a number here, it always means square root. But if it is the third root, then it would be like a to okay, the third root is the same as cube root. So this would be 3. So square root has a 2 here, nth root has n here. If you have 27 to power a third, this is equivalent to what number can I raise to a power of 3 and it is still equal to 27? It's going to be 3 to power 3. So I again raise it to a power of a third. This is the same as saying 3 to power 3 times a third, and this is equal to 3 to power 1, and that is 3. So now let's look at if we have any number to power 0 is equal to 1, and this is true if the number is greater than 0. I'm saying if I have a to power 0, this is equal to 1. And this is only true if a is greater than 0. If it is not, then 0 to power 0 is equal to indeterminate. It is an indeterminate solution. So for us to have any number to power 0 that and is equal to 1, that number must be greater than 0.